In section 5.2, we're looking at polynomial functions and adding and subtracting polynomials. Our objectives are to define polynomial, monomial, binomial, trinomial, and degree, define polynomial functions, simplify a polynomial by combining like terms, and add and subtract polynomials. Let's find the degree of each polynomial and determine whether it is a monomial, binomial, trinomial, or none of these. In the first example, x squared plus x minus 6, we say that the degree of this polynomial is 2. And we can say that because the highest exponent of just the first term, x squared, has an exponent of 2, so the degree of that polynomial is 2. Now, since this has 3 terms, we can say that this polynomial is a trinomial. Just like a tricycle has 3 wheels, this polynomial has 3 terms, so we call it a trinomial. In the second example, we look at the exponents of the variable bases. Now, the first term is 3x plus 10, and x we can think of as being raised to the first power. So the degree of this polynomial is equal to 1, because that exponent in the first term is 1 and there's only a single variable. Now we can also see that this polynomial has 2 terms, so we can classify that as a binomial. Just like a bicycle has 2 wheels, this polynomial has 2 terms, so we can call it a binomial. Now the way that we figure out in example C the degree of the polynomial is looking at the exponents of the variables. Now this is all one term, so the degree is actually found by looking at all those exponents in that single term and adding those together. So the degree is 3 plus 2 plus 1, which is 6. Again, we're looking at the variable exponents of that single term. 3 plus 2 plus 1 is 6. And this polynomial has only one term. This expression, we're not adding or subtracting any other terms, so since it's a single term, we can classify this as a monomial. Like mono means one, singular, so this polynomial has one term, we can call it a monomial. In example D, we have 8z to the 5th plus 9. The degree of this polynomial is 5 because the greatest exponent that we see in the first term is z to the 5th, the exponent of the variable base. And since this has 2 terms, we can call this a binomial. In this example, we're identifying the degrees of the terms and the degree of the polynomial. So we look at each individual term. In the first example, we'll begin with the first term is 2xy. And then we'll list the degree of each of those terms and then list the degree of the entire polynomial. Since the first term is 2xy, we can think of this as x to the first and y to the first. So the total degree of that first term is 2. 1 plus 1 is equal to 2. The second term is our negative 5x. We can think of this x as just an x to the first. So the degree of the second term is 1. The third term is 6xy, which is a 6x to the first and y to the first. So the degree of that third term is 2. Now we're looking at the degree of the entire polynomial. So the entire polynomial, the degree is whichever is the highest. In this case, the polynomial entirely has a degree of 2. Let's look at the second example. We're going to look at 4a to the 3rd. That's our first term. So again, we're looking at the term and the degree. Maybe easier to make it as a table. So our first term is 4a to the third, and then we're looking at the degree. The degree is the largest exponent, so the degree of the first term is 3. The second term is minus 3a, and that has a degree of 1. And then the last term is that plus 6, or just 6, and that has a degree of 0. And we can consider that 0 because 6 by itself can think of as 6 times a to the 0, where a to the 0 is equal to 1. Now let's look at the degree of the entire polynomial. This has polynomial, and for the entire polynomial, we're looking at just the greatest degree of any individual term. So this second example, the entire polynomial has a degree of 3. For the third example, let's look at the terms. The first term and the degree. First term being x to the third y. Now x to the third, that variable is 3. Y by itself is just y to the first, so the degree is 3 plus 1, which is 4. For the second term, that negative x squared y squared, we're looking at the degree of the term by adding those variable exponents. We get this degree of the second term is 4. And then the last term, the xy to the third, x by itself is an x to the first, so that has a degree of 4. For the entire polynomial, the degree is equal to 4. And then finally, for the last example, let's look at the first term, which is s to the fifth t to the second. And then the corresponding degree is 5 plus 2, or 7, for the first term. The second term, negative 3s to the fourth t. This is s to the fourth. We're looking at 4 exponent, and t by itself is t to the first, so 4 plus 1 is 5. The last term, that 5st, s by itself is s to the first, t is t to the first, so the degree of that term in the entire polynomial, degree of that term is 2. So for the entire polynomial, the degree is that highest degree of 7. We want to evaluate each polynomial for p of 0 and p of negative 2. Now if you're following along with the handout that's included with these videos, there was a mistake. So the original polynomials were p of x equals 4y minus 7. Change those y's and all of those polynomials to an x. X is our input variable. So whatever we're plugging into x, we want to make sure we plug it into all of the x's. So it wouldn't make sense to have p of x equals something with a y in it. So make that correction and follow along. We want to start with example A. P of x is equal to 4x minus 7. So we want to evaluate p of 0 by replacing the x in the original polynomial with 0 and then simplifying the answer. P of 0 would be 4 times 0 minus 7, or 0 minus 7, which is equal to negative 7. So the first answer for part A is p of 0 equals negative 7. Now let's continue and find p of negative 2. To find p of negative 2, we replace the x in the original polynomial with negative 2 and simplify the result. So we multiply 4 times negative 2 to get negative 8, and negative 8 minus 7 is equal to negative 15. So p of negative 2 is equal to negative 15. So we're going to have two answers for each part. P of 0 is negative 7, and p of negative 2 is negative 15. Let's continue with example B. Here our polynomial is x to the third minus 4. So p of 0 is going to be found by replacing the x with 0. 0 to the third minus 4, which is 0 minus 4. So we get p of 0 is negative 4. So when you enter 0 into the input, the x value, what you get out is negative 4. Let's find p of negative 2. or replace the x with negative 2, so we get negative 2 to the third power minus 4, and negative 2 to the third power is negative 8, and negative 8 minus 4 is negative 12. So p of negative 2 is negative 12. In example C, we want p of 0, so it's going to be 3 times 0 squared plus 8 times 0 minus 9. And when we simplify that, it's going to be 3 times 0 is 0, 8 times 0 is 0. So p of 0 is equal to 0 plus 0 minus 9. P of 0 is equal to negative 9. Let's find p of negative 2. So it's going to be 3 times negative 2 squared plus 8 times negative 2 minus 9. Remember the order of operations. We always want to do those exponents before we multiply. So this is going to be 3 times negative 2 squared, where negative 2 squared is equal to 4, plus 8 times negative 2 minus 9. Now that we've done the powers of the exponents, we can do the multiplication. 3 times 4 is 12. 8 times negative 2 is negative 16 minus 9. And then we can solve this, simplify, combine those like terms. 12 minus 16 minus 9 is negative 13. So p of negative 2 is equal to negative 13. For part D, p of x is equal to negative 13 minus 4x minus x squared. Let's find p of 0 by replacing the x's in the polynomial with 0. We get negative 13 minus 4 times 0 minus 0 squared. So when we simplify, we get negative 13 minus 0 minus 0. So p of 0 is equal to negative 13. And then p of negative 2, that's going to be negative 13 minus 4 times negative 2 minus a negative 2 squared. Be careful with the signs there. Let's do the exponents first. Negative 13 minus 4 times negative 2 minus a negative 2 squared, so it's going to be minus 4. Now we can multiply the middle term. Minus 4 times negative 2 is going to be plus 8. So we get negative 13 plus 8 minus 4. So p of negative 2 is equal to negative 9. For these examples, we are going to simplify each expression by combining like terms. In order to have like terms, you must have the same variable and the same exponent. So when we look at example A, 3x minus 10x, since these are like terms, they both have just the variable x, no other variables, same exponent. So this is going to be the same thing as 3 minus 10x. By 3, I have 3x and I take away 10x. The result is negative 7x. So we have simplified that expression by combining the like terms. We'll continue combining like terms in the second example. We have 3y cubed minus 6x squared plus 2x squared minus 5y to the third. So the 3y to the third has another like term, which is the minus 5y to the third. We can combine those two because they have the same variable base and the same exponent. On the other hand, we have the negative 6x squared. The other like term that we can combine with that is the plus 2x squared. So let's begin by combining the x terms. The negative 6x squared plus 2x squared, and then we'll combine the y terms, the 3y cubed minus 5y cubed. By combining those like terms, we have the negative 6x squared plus 2x squared. When we combine those, we combine the coefficients to get negative 4x squared. And then by combining the y terms, the 3y cubed minus 5y cubed is minus 2y cubed. So our final answer is negative 4x squared minus 2y cubed. In example C, we have 3.7x to the third minus 6.3x plus 11.6 plus 1.8x minus x to the third minus 8.2. Let's highlight the like terms so we can combine only those like terms. To begin with, I have the 3.7x to the third that can be combined with the minus x to the third, only because you have the same variable base x and the same exponent 3. We can also combine the minus 6.3x with the plus 1.8x. Again, those both have the same variable base, the same exponent of 1. And then finally, the plus 11.6 can be combined with the minus 8.2. We call those constants. There's no variables in them. So let's go ahead and group those, combine like terms to simplify the expression. Let's begin with the x cubed terms. So we have 3.7x to the third minus the x to the third. We'll combine those. And then we have the minus 6.3x plus 1.8x. And then we'll combine those constants, 11.6 minus 8.2. I'm going off the page there. So let's combine the x cubed terms. 3.7x cubed minus 1x cubed, that's the same thing as 2.7x cubed. Okay, then we have the x terms, the negative 6.3x plus 1.8x. We're going to take a negative 6.3 plus 1.8 to get a minus 4.5x. And then finally, our last constants, we're taking 11.6 minus 8.2 to get a plus 3.4. So that is our final answer. We've simplified the polynomial expression by combining like terms. Okay, for these examples, we're going to perform the indicated operation. In example A, we have the quantity 4x minus 3 plus the quantity 2x minus 7. I'd like to get rid of any parentheses first if there was anything I needed to multiply by. It looks like I can rewrite this expression as 4x minus 3 plus 2x minus 7. Now I can combine like terms. I can combine the 4x with the plus 2x. So 4x plus 2x, I'm going to combine those together, and then I can also combine those constants, minus 3, minus 7. When you combine those like terms, 4x plus 2x is 6x, and the minus 3 minus 7 is minus 10. So our solution, our simplified expression, is 6x minus 10. Let's continue with the second example, where we have the quantity 5x squared plus 3x minus 7 minus the entire quantity of negative 5x minus 3. So in this case, we need to distribute that negative before we can combine any like terms. So I'll begin with writing the first 5x squared plus 3x minus 7, and then this minus a negative 5x is the same thing as plus 5x, and minus a negative 3 is the same thing as plus 3. Now I can combine like terms. I only have one x squared term, so I'm going to leave that as 5x squared, and then I can combine the x terms of plus 3x and plus 5x, and then I can combine those constants, the minus 7 plus 3. When I simplify that, the first term is 5x squared, the second and third term are like terms, so we can combine those. 3x plus 5x is 8x, and then the last two terms are constants. Negative 7 plus 3 is a minus 4. So our solution is 5x squared plus 8x minus 4. In the last example, we want to subtract the quantity 3x plus 2y from 5x minus 7y. So we want to rewrite this as the quantity 5x minus 7y, and we're going to subtract 3x plus 2y from that 5x minus 7y. So it's important to write it in this order. And then we will be distributing this negative sign and eliminating the parentheses to get 5x minus 7y minus 3x minus 2y. Now we can combine like terms, beginning with the x terms, 5x minus 3x, and then the y terms, minus 7y minus 2y. By combining those first two terms, 5x minus 3x, I get 2x, And then combining those last two terms, negative 7y minus 2y is negative 9y. So that is our solution. To simplifying that expression, we have 2x minus 9y.